just like a small, it's a doctor who does a private practice on one side, and then on the other side it's the research center. Yeah. I'll stop talking, you can start.
No, that's all right. I was actually just going to start with some review. So, what is the molecular structure of XEF4? What is the electron geometry, as well as what is the molecular geometry?
There's nothing on the screen.
Oh. No, I do not want to shut it down. So there you go. XEF4. What is the electron geometry, as well as what is the molecular geometry?
Tetrahedral. Oh wait, I thought this was participatory.
No, that's fine. No, it's not tetrahedral.
Okay.
So xenon, if you actually, let me pass out some periodic table as well if you don't have one with you. So for one, it is not a tetrahedral structure. Xenon is a noble gas, so it has 8 valence electron.
Thank you.
And that's for Anthony. So if you look at your periodic table, xenon, most of the time, regardless what method that you do for Lewis diagram, most of the time, you always start with yes on that one. Most of the time, you always start with counting the number of electrons. So 8 plus 4 times 7, this is 28, so we have 36. And then, in my longer way to go, we make a guess on how many electrons in the center. So all of the fluorine would like 4, 8, and there's 4 of them. And I'm going to guess that this is going to be 12. Somewhat educated guess, because I've seen this before. So 8 times 4, 32, 44. The difference is going to be 8 divided by 2, so that's 4 bonds. Right, so that tells you that there's going to be 12 electrons in the center. So if there's 12 electrons in the center, what is going to be the electron geometry? If there's 12 electrons in the center, that means there's 6 lobes sticking out.
There's number 6.
Right.
Square pyramid.
No.
Octahedral.
That's the, right. It's going to be octahedral.
And then the other one is square planar.
Yeah. Yeah. And then more or less the molecular structure looks something like this. XE, F, F, sticking out to the front, fluorine on that side, and we have a couple of double bonds in the middle. There's a lot of different ways that you can try to do this. Obviously, I like my own ways, but if you're okay with other stuff that you watch online, then that's perfectly fine with me too. Is this molecule polar or non-polar? Yeah. That's because they're completely symmetric on the top, as well on the bottom, and then left, right, and so on. They're completely symmetrical. So it's going to be non-polar because it's symmetrical. So that's that. This is probably as harder as it gets in terms of molecular geometry and so on. Another typical thing that I might ask is if I were to give you SF6, XEF4, NH4 plus BRF5, which one as is or are tetrahedral. So if we were to switch around in terms of rather than drawing it and ask the question tetrahedral molecular geometry into a multiple choice type questions, and I could ask something along this line, or which one is seesaw shaped and things like that. So, or actually in this case there's no seesaw, but yeah, you get the point. So the variety is that if you can do it for one molecule, if we have to convert it to multiple choice question, then that's going to be the typical thing that you'd be asked to do. So that's a bit of review on the Lewis diagram stuff. Let's see, what else should I review? Which of these structure is a more stable one? A is going to be HCN. B is HNC. Which one is more stable, and what's the argument for it? Yeah.
Charge on the most electronegative atom.
This is where I calculate formal charge,
Right, so that's where the formal charge comes in. So what's a formal charge on hydrogen?
It's 1,
0. The formal charge, you always want to calculate the formal charge if you have a question that looks like which one is more stable. And the formal charge is the number of valence electron minus the number of bond. I should say the number of lone pairs minus bond. Depends on how you count it. So if you count the number of lone pair electrons, then it's a slightly different things. But they do mean the same thing. So for hydrogen, the valence electron is 1. The number of lone pair around the hydrogen here is 0. And the number of bond is 1. So 1 minus 0 minus 1 is equal to 0. So that's why the formal charge for oxygen is 0. Hydrogen is 0. There's also an easier way, somewhat slightly faster way, that you can look at the formal charge based on the number of bond if you remember where they are in the periodic table. So I think 1, 2, 3, 4, 5, 6, yes. So the general trend is that everything on this side here is more likely going to have a +1 charge. Then this is going to be +2, +3, plus and minus 4, -3, -2, -1, 0. We've done something like that before, right? So the preferred number of bond is going to be preferred number of bond. And it's going to be 1, 2, 3, 4, 3, 2, 1, 0. So the noble gas usually doesn't have any bond. And as long as you see that the preferred number of bond is exactly the number of bond that you have, then the formal charge is going to be 0. So what is the preferred number of bond on carbon? 4. So carbon preferred to have 4 bonds. And in this particular carbon, there's 1, 2, 3, 4 bond. Without doing too much calculation, you can find out that the formal charge of this carbon is 0. And then if you look at nitrogen, which is going to be right... Oh, hold on, the other way around. Nitrogen is right there. Nitrogen prefer to have 3 bonds, so if you try to count the number of bonds around this particular nitrogen, there's 1, 2, 3, so 3 bonds, 0 formal charge as well. So there's a few things that you can do if you remember the trend in the periodic table that you don't have to manually calculate every single one of these.
What's the trend on top? I know the bottom is the preferred number of bonds.
Oh, this is most likely charge.
Most likely.
So hydrogen is most likely going to have a +1 charge. On some occasion, and when it's bonded to a metal, it's actually going to be a -1, but that's a different thing altogether. And you're going to find that majority of the time, if the number of bond that you have is not equal to the preferred number one, that's when your formal charge is not going to be 0. So whenever you see something like this, like nitrogen prefers to have 3 bonds, but it has 4, try to calculate the formal charge, because that's when it is going to be positive or negative. So let's do the calculation on the nitrogen, as well as the carbon in the end. Because the first one, well, I guess to answer the first question, which one is more stable? That's going to be more stable just because all the formal charges are 0. The formal charge on the hydrogen here for B is also 0, but for the nitrogen, the valence electron is going to be 5, the number of lone pair electrons is going to be 0, and the number of bond is going to be 4, so this is +1. And when you look at the formal charge on the carbon, the valence electron is 4. The number of lone pair electron is 2. That's the 2. And then we also have 3 bonds in total, so this is going to be -1. So the total formal charge is -1. This is going to be less stable because that means this particular carbon gained more electrons than what it could stably hold around its nucleus, so it's not that stable. Any review on this one? No? Pretty straightforward?
I had 2 questions on the previous.
Oh, okay.
Sorry, they're quick questions.
What was the previous one? Xenon?
The tetra, well, yeah, the xenon
Oh,
one.
yeah.
Can you go over the way you did the preferred again, please?
This one?
Yes.
Okay.
Sorry.
I guess that it's 12.
You got, because you can guess up to 12.
You can guess up to 12, and then I know that there's 4 fluorine, and I have 4 bonds, so that's good, because I know fluorine, each one of them prefer to only have 1 bond. So,
Okay.
I know that there's 4 fluorine, so it must have 4 bonds at least, so that's where we go.
Okay. And then the second one, for the refractory tetrahedral, is it the xenon F4 and the NH4 plus?
Nope. That's a good, useful process of elimination. So if you have a tetrahedral, you need to have at least 4 atoms attached to it. So we can immediately eliminate these 2. So xenon tetrafluoride is not tetrahedral. We just did this one. This was square planar.
Yeah.
So, so the only one that's actually tetrahedral is NH4 plus.
Okay. Thank you.
Some process of elimination is useful too. Okay, so the last portion of the class is basically just nomenclature and just trying to remember how to name one molecule to the next Yeah, we've already gone through that. Sorry, Angel, I didn't have my connector, so it wasn't recorded at all. Oh, one last one that's kind of useful just because it shows up all the time. Sorry? No. This is the Lewis diagram of a molecule called benzene. You'll learn that way after. So count the number of sigma bond and count the number of pi bonds. How many pi bond? Pi bond is easier.
3.
3. Because you have 3 double bond here. 1, 2, 3. So each of these is going to be a pi bond. And how many sigma bond in total?
12.
Yeah, 12. So the sigma bonds, let me use a different color. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm missing one more, but it should be 12 in the end.
The double bond C on the right.
Ah, yeah, I'm missing that one. Cool. So just remember, the first bond is going to be a sigma bond, and then the second and the third is going to be a pi bond. And what I meant by that, this particular bond here is a double bond, so it's going to be contributed, it's going to have one sigma bond and one pi bond associated with it.
That means that will be a hybridized bond?
Yes. So that's a follow-up question. What is the hybridization around this carbon? Or actually, you were going to say something? No. All right. What's the steric number around this carbon? Steric number? How many stuff is attached from this carbon? You see that there's 1 atom, 2 atom, 3 atom, and there's no lone pair. So the steric number is 3. And whenever you have a steric number of 3, you will have sp2 hybridization.
So the steric number, because I saw not maybe like said E plus X.
Right.
Are they just counting how many atoms are attached?
Right. So the steric number, the equation that's on there is E plus X. The X here is the number of atom. E is the number of lone pairs. Not the lone pair electrons, just the number of lone pairs.
Okay, the pair. Oh,
Pair, a pair. So sometimes it's lone pair electrons and sometimes it's lone pair. So in this particular case, for the carbon that we're talking about, this particular carbon here, there's no lone pair and there's 3 atoms attached to it, so the steric number is 3. And if you look at your table, the Vesper table, steric number 1, 2, 3, 4, 5, all the way to 6. If you look at the steric number 3, this is going to be sp2. Or if you want to look at it this way too, so there's 3, so that means there's 3 orbitals combined. So one is s, the other one is p, and the other one is also p. sp2 hybridization. Or if you want to look at it as this is a double bond, all double bond is sp2 majority of the time, that's fine too. Either way. So the other thing would be, what is the molecular geometry around this particular carbon? Close. It is trigonal. Yes. Trigonal planar. Yeah. Majority of the time, the shape will give you the name as well. So. Alright, so that was the questions on the benzene. We've done hybridization, pi, sigma bond, molecular geometry around each of the carbon. Alright. And
we don't need to know angle.
No. And okay, so this is what I want to go to next. Just chemical bond polarity as well as how to name them. And we distinguish an atom as either a covalent molecule or ionic, depending on whether or not they share their electrons with one another. Did I do this last week? Not really. Okay. So, and the best way to know whether something is sharing electrons or not is when you want to look at their difference in electronegativity. And what's the order of 9 most electronegative elements? Falkland-Birch. Thank you. Falkland-Birch CH diagram. Sometimes people forget the I, but it's right there. And if you look at your periodic table, one of the back pages should have like the list of the electronegativity of the elements. There's none on the noble gases because they pretty much have zero electronegativity, or very close to zero. And essentially, if your electrons is shared, it's going to be covalent, and if it's not shared, it's going to be an ionic one. And we will look at it based on the electronegativity. So let's look at the simple case first. So let's look at a hydrogen and chlorine bonded together. So if we look at our order and Falkland burst, Cl is right here, chlorine is right there. So they're actually quite different in terms of electronegativity. And if you want to look at the numerical value, we have 3.16 on chlorine, and for hydrogen it's going to be lower, 2.20. So clearly there's the electronegativity is not the same between one with the other. So you can think of this thing or this particular molecule of having chlorine, because it's much more electronegative, it's going to pull electron towards itself much greater, with much greater force compared to hydrogen. So you can think of it as that's the elephant. And hydrogen is actually one of the lists that have a pretty decently high electronegativity. So let's think of this as a horse. Yeah, that's a horse. And they're pulling rope. And obviously the elephant is going to win because it's much more higher in electronegativity. And what it simply means is that when you look at their electron density, it's going to be some sharing occurring, but it's not going to be an equal share. That is, majority of the electron is going to be taken up by the chlorine side. Right? So when you're looking at whether a molecule is polar or nonpolar, we look at their electronegativity difference as well. Same concept here.
Just to reiterate, the electronegativity increases up going up the periodic table and to the what?
I think it's diagonal.
Yeah.
It's diagonal. Something like that. That's your electronegativity. And fluorine is right here, which is why it's the highest one. Or the highest one that we have. Yeah. So I think that's a correct order. Now here, what we have here is an unequal sharing. And when the sharing is unequal, we call this a polar covalent molecule. It's still covalent because the electron is still is shared between the hydrogen and the chlorine, but it's an unequal sharing of electron. We can also have a case where the electrons are entirely shared equally. So for example, if we were to have two chlorine bonded together, we can think of this as, well, if we look at one chlorine as an elephant. Oh, what happened there? We can think of two chlorine bonded together as having two elephants, exactly the same size, exactly the same shape, pulling the rope together, so none of them will win because they pull it exactly the same strength. Because they pull exactly the same amount, so the electron is going to be shared pretty much equally between the two. And when you have equal sharing, we call it a nonpolar covalent. Again, it comes out to, well, we have two chlorine here, it's symmetrical, so it's nonpolar. but the electron is still shared, so non-polar covalent specifically. And there's one last case where we have two molecules where one of them is, let's just say, chlorine. So we have an elephant again, because it's fairly high in the electronegativity table. And we have a sodium, Na, and if you look at the number for sodium, it's 0.92, and chlorine it is 3.16. So sodium, you can think of it as a person, and when they pull rope, the rope is just going to get dragged out by the elephant because it's so much greater in electronegativity or in much force. So what happens is that instead of having a share of electron, in this particular case where the difference in electronegativity is too high, we don't have any sharing, but instead all the electron goes out from the sodium. So the sodium becomes positively charged and the chlorine becomes negatively charged because the electron just taken up completely, no sharing. Because the difference in electronegativity is too large. Element with higher electronegativity will take the electrons entirely. Okay. And so, any question in terms of the general mental picture that we have for the whole process? Ionic. Yes. Right. So when there's no sharing, because the electronegativity difference is too large, then we call it an ionic molecule. No sharing of electron. There's actually one more, which is metallic, where the electrons is shared between many atoms. But that's a whole different thing altogether. The reason why aluminum or most metals are metallic is because the electrons are not just shared between one aluminum atom to another aluminum atom. It's not just a single bond. It actually propagates throughout the entire large chunks of atom. That's why they conduct electricity, because all the electron is being shared. But metallic bond is not that interesting, at least in molecular chemistry for now.
Is that why gold is such a useful, like electronics? Not only it has unusually
Gold? No. Not really. Not really. Mostly gold is, if you use gold in electron circuits, usually because they're, one, they don't corrode. The other is, I'm trying to explain. It has a lot to do with their work function, and when you connect a semiconductor to a metal, you have to match their work function, but it's kind of beyond the scope, I think, of our class. Okay. No, you have enough information. So if you have a semiconductor, you have, it's basically the same picture that we have before. We have molecular diagram, and what you see in LED light, some LED is blue, some LED is red, and so on, is that if your molecular orbital energy levels, where this is one electron, this can fit another one, if the energy difference is large, you get blue color, and if the energy difference is small, then you get red. Right, so that's what you learn from part 1. But this, instead of an atomic orbital, this is a molecular orbital. So it's the same molecular orbital that we have there, but now it involves much more complicated looking shape. Now, one of the reason that you use gold and so on is that to connect it with one with the other one. If you look at the electronegativity, actually you're not looking at the electronegativity, you look at what they call the work function, which again, it's the amount of energy needed to remove an electron. You want to make sure that the metal, if let's say you want to make sure that the electron flows in this particular direction, that is, you want to have the electron flow from the gold into the semiconductor and then pass through the other side, then you want to make sure that the electron energy is a little bit higher on the metal side, so it kind of flows like gently down the hill. Whereas if you're using a different metal with a different low work function, what happens is that the electron needs to go up in energy in order to flow through. So that's basically adding a resistance to your circuit. So because this thing needs to go up in energy, that means you need to spend extra energy, which makes it less efficient. It's within the scope of what you've learned before. It's just now application rather than rather than the basic science of it. The basic science is not beyond what you've already known. We're just now getting into the details.
I have a question just about a sign that I want to put on the lower electronegativity versus the higher electronegativity.
Yep.
You know, for the polar and non-polar, we did the plus with the arrow
Mm-hmm.
to signify
Mm-hmm.
electronegativity. Can I do that here too? Or is that
Yeah.
just different?
No, it's exactly the same thing.
Okay.
So let's just say this is H is the blue one and Cl is the red one. Chlorine is more electronegative. So when it make a bond, hydrogen is going to be a little bit more positive. Chlorine is going to be a bit more negative. So it's the same thing.
I just wanted to confirm that.
Yeah.
And then when it's like chlorine, you don't put any.
Right. So here, if we have 2 chlorine, then they pull exactly the same amount. So no arrows in the end. They're completely symmetrical. So yeah. There's a bit of a cutoff between what is considered ionic. Some textbooks says it's 1.8 to 3.3. Sometimes people just kind of round it up to 2 and above, but it's kind of arbitrary in a bit. So there's no particular exact location, but 2 is a good number to remember. And then anything below is going to be covalently bonded. So above 1.8 in this case is going to be ionic. And then anything below is going to be covalent. Right? And then we also make a slight barrier between what is considered nonpolar versus polar, and that's usually between the 0.8 region, 1.8 to 0.4, and then anything below 1.4, we consider them as entirely nonpolar. But again, sometimes it's the where we take this cutoff is a bit arbitrary. It really depends on the actual shape of the molecule once it makes a bunch of bonds.
So you don't want this.
It's useful to know that, you know, less than 1 is going to be considered nonpolar, whereas somewhere between 1 and 2 is polar. It's a good part to remember. Or if you want to go to 0.5, that's fine too. 0.5 to 2 is also fine if you want to remember it that way. In any case, there's a breakdown. It's a degree. It's just a degree of sharing. And if you, it's just a degree of sharing. Now the implication in terms of this whole thing is for the second part of the exam, I just want to go into the part where they're named slightly differently. That is, if we have a covalent molecule, the naming structure is going to be different than if we have a naming for an ionic molecule. Different name. We can go for the covalent one first, and they're pretty straightforward. You just add the non-central atom ends with an "ide," and then the central atom add prefix to it. So, for example, if we have PCl5, we have 1 phosphorus and 5 chlorine. So we're going to call it phosphorus, penta for 5, chloride, and we simply end the word with an "ide" in there. And then, this one here is dichlorine heptaoxide, although sometimes people call it also dichloro, is a common vernacular that people use as well. Mostly just for the halogen, so instead of fluorine, it becomes a fluoro, chlorine becomes a chloro, bromine becomes a bromo. But if you write it down this way, I'll be happy with it. Anyway, mostly because the chloro is a bit easier to pronounce, I think. It just rolls out the tongue better. And then the prefix that you're going to use is also fairly straightforward. Mono is 1, di is 2, tri is 3, tetra is 4, and so on. So the covalent one is actually pretty straightforward. It's really easy, but the only one that's a bit more confusing is the name for the ionic compound. And I'm going to split it up again. If this is not a transition metal, then you don't have to do anything with it. Just the metal is the same, whereas the non-metal is just going to end with an "ide, unless it's a polyatomic compound. The naming is simple. So for example, if I have NaCl, we're going to just name it sodium chloride. If we have magnesium chloride, MgCl2, the name is still magnesium chloride. Right. So the only difference here is that we're just going to change the ending on the chlorine into chloride. If it's an oxide or oxygen, it will be an oxide, nitride, and so on.
And this is because it should be obvious with magnesium chloride, you would have two chlorines because magnesium is...
Right. Magnesium. And the reason why we don't do anything is because magnesium always a +2 charge. And it's one of the things that's not transition metal, so this is +1, where the sodium is located. +2 is where the magnesium is located. So magnesium is always +2, so you don't really care about it. But if you do have transition metal, antonite, lactonite, and so on, sometimes the metal can have multiple different charges. So when you have transition metal, actinide, lanthonite, and so on, so anything that's not the main group element, they can have can adopt multiple possible charge. So you would have to give it a Roman numeral to indicate charge. And for example, the easy one would be iron, since we use iron all the time. If the iron have a +2 charge, this is going to be called iron 2 with a Roman numeral 2. And if the iron have a +3 charge, then this will be an iron 3. Right. So, but otherwise the naming is also very similar. If we were to have an iron 2 oxide, the formula would be FeO, and if we have an iron 3 oxide, the formula would be Fe2O3. What I'm trying to get to is that whether it's iron 1, or sorry, iron 2 or iron 3, you can see that the molecular formula is different. Hence, the Roman numeral here is going to be important. The last one that I want to mention is that how to balance the molecule for these metals or ionic molecule, and they're also pretty straightforward. You want to make sure that the sum of the charges equals to 0, because same reason with the formal charges. When you have a sum of 0 charge, it's actually more stable. And the easiest thing to do is that if you have iron 3 plus, and an oxide is always a -2, 3 and 2, so the easiest thing that you can do is just make a little bit of a cross. So this becomes Fe2O3. So you want to make sure that the sum of the charges is 0. That's all that we're looking at. And if we have 3 plus times 2, so this becomes plus 6, and we have -2 on each oxygen, and we have 3, so this comes out to -6, and we add it up together, it goes out to 0. And if they're not ionic anymore, then they're pretty stable overall. So that's about it in terms of the summary of the nomenclature. We'll get into the acidic one in a bit, but I think once you look at some of the example, it'll be pretty straightforward for the acids as well. The best way to learn about nomenclature is not trying to memorize the rule, just try to write it down. And so we'll go on this particular sheet, finish off everything on number 1 and number 2 because they're easy. Try to do some of these, and especially these last 4 boxes on the corner. If you manage to do those perfectly, that means you can probably skip to the next portion. And yeah, once you think that you have a hang of on the rule, let me know. I'll check it. Then we'll go from there. Let you guys go for today. So summary for exam number 2. So for 1, the basic is that I want you to be able to do the Lewis diagram. So draw the Lewis diagram. Then figure out which one is most stable. If you want to know which one is more stable, you need to know the formal charges. And once you've done with the Lewis diagram, I want you to be able to figure out the electron geometry as well as the molecular geometry. And while we're at it, I want you to be able to identify whether they're polar and non-polar. So Lewis diagram, most stable. Now, so that's kind of the basic stuff. The more quantum mechanical portion is I want you to be able to understand what is hybridization. And the different kinds of hybridization as well. So identify which one is which one is an SP, SP2, SP3, SP3D, and SP3D2. And most of the time, you know, if you realize that the steric number is 3, 4, 5, 6, that's kind of the same thing. Although the SP hybridization here is a little bit hard to see. Or if you want to think about it, whenever you have a triple bond, you have an SP hybridization, and then if you have an SP2 hybridization, this is going to have at least one double bond. Not always. It's not going to be this exactly all the time, but it's pretty close. And then if you have a double bond and triple bond, I want you to be able to identify the number of the sigma bond as well as the pi bond. So I want to be able to count. Oops, somehow it disappeared. Oh well. Count sigma and pi bonds. And I wanted to be able to draw them as well, the sigma and the pi bond. So yeah, if I were to say this is a sigma bond between s and p orbital, then it would look, something like that, for example. That's what we had last time. If we have a sigma antibonding between s and p, then we would have, maybe something that looks like that. Right, so I want to be able to draw these as well. So this is a more quantum mechanical portion of stuff. And I want to be able to draw the pi bond, or the pi antibonding, and so on. So, draw the orbitals, both the bonding and antibonding. So we're going to go increasingly more quantum mechanical stuff. And I want you to be able to construct the MO diagram for simple molecules, so diatomic molecules like H2, helium-2 type thing. We did O2, N2, F2 type things, and I guess those are the more common one. And remember, I should put it away this way, N2 and O2. Remember, at somewhere around here where it splits, the energy diagram gets split around between one to the other. So make sure that you remember that one. And then from the MO diagram, you should be able to determine the magnetism as well. And then just kind of also, since you're constructing it, you should also understand what it is. What is the MO diagram? What else?
For the structure.
Oh, right, nomenclature. Shoot, I forgot about that.
A question about the MO diagram test. I know you're saying construct for the simple molecules, but are you going to go crazy with the anti-bonding?
No. Both the bonding and anti-bonding? What do you mean?
Like when they have the MO diagram and it's the anti-bonding and the bonding by sigma.
Well, if I were to just give you anti-bonding between a p orbitals and something else, you should be able to construct that easily. What I meant by constructing it from scratch is this one here. So, where you have to make this diagram. And kind of, if you understand what it is, you should also be able to interpret it. Some of it. Which goes back to exam 1 a bit. It's interconnected, so you do want to know what those are. So, okay, so that's mostly it, I think. Lewis diagram, formal charges, electron geometry, molecular geometry, polar, nonpolar, hybridization, drawing the orbitals and the diagrams, the shapes of it, the MO diagram that looks like this, and what it is, how to draw them, count them, bond order. Oh, I should say magnetism and bond order, but that's not that hard to do.
So the nomenclature, the naming, and then writing them out like this too.
Well, which one is that?
Where you cross them.
Yeah. So that's part of.
What we talked about the end was for the next test, like the concentration and everything.
Yeah. The concentration, the molarity that we got, we went through just then, just now is for the next step over. Not yet. We're still just comprising or constructing things, simple molecules, and then how to name them is the end of exam 2. Right. Any clarification? Nope. Yeah. So, before I forget, do turn in the correction if you want to submit one correction.